In this presentation, we consider some examples of AC parallel resonance circuits. So in this particular example, we have a current source that is 3.6 milliamps, phase angle of 0. Of course, there is some voltage across that current source because these are all connected. The resistor, the capacitor, and the inductor are all connected in parallel with one another. And so we're going to answer a few questions regarding this particular circuit, and we're going to look at resonance and see if we can figure out the resonance frequencies, quality factor, and some other things. So the one thing I did want to mention about this particular example is that we are assuming that we have a perfect inductor and that it does not have any coil resistance. So we're starting with sort of an easier example, and then we're going to approach this where we actually have an inductor that has coil resistance, and then how we would go about looking at that particular case. So this case, pure inductance here with no resistance. So we want to determine the resonance frequencies, both in radians per second and in hertz. We want to figure out the quality factor for this resonant circuit. We're going to calculate the voltage across the circuit at resonance. We're going to find the current through each of the components. We're going to determine the bandwidth, and we're going to maybe sketch what the voltage response would look like and the power sensitivity curve. So the first thing that we have to realize is, as I mentioned, that the resistance of the coil in this particular circuit is 0, and the impedance is pure. The reactive impedance is pure inductance. That's kind of a weird way to say it. So that the way this is worded is a little bit strange, but there's no coil resistance. The impedance is all going to come from the resistive piece, and this particular impedance for the inductor is purely resistance. So we're going to determine the resonance frequencies, and so the coil resistance. So we know that for parallel resonance, the resonance frequency is 1 over the square root of the inductance times the capacitance, and then we also have this other component that depends on the coil resistance. In our particular case, the coil resistance is 0 for this example. Again, this is like the perfect inductor situation, and so we can determine what the resonance frequency would be. And we can plug in what the inductance is, which is 0.016 Henry, and the capacitance 0.4 times 10 to the minus 6 farads, and I get 12,500 rads per second. I have a feeling I did not convert this into frequency in hertz, but I could take that number and divide by 2 pi, and I would figure out what that frequency is in hertz. I can also determine what the quality factor is, and so the parallel quality factor would be the resistance over the inductive reactance. And so the resistance is 500 ohms. I can figure out the inductive reactance because it will be 12,500 rads per second times the inductance, and I end up getting 2.5. So my quality factor is 2.5. And remember, the quality factor is going to tell us something about how the current, the maximum current through the capacitor and the inductor is related to the current of the source. So I know the capacitive reactance is equal to the inductive reactance, and we found that well, we didn't find it, but I use this expression. It's the angular frequency times the inductance if I'm looking at the inductive reactance, and I end up getting that that is 200 ohms. So I want to keep that in mind as I move forward. I want to calculate what the voltage is across the circuit at resonance, and I know that the voltage is just the current of the source times the resistive impedance. Because the capacitive reactance and the inductive reactance are equal to one another, they cancel each other out. So all of the impedance in this circuit is coming from the resistor at resonance. So this would be the current times the resistance, and I went ahead and I wrote down the resistance in kiloohms because milliamps times kiloohms is going to give me volts. So I get that the voltage across any one of these components at resonance is 1.8 volts with a phase angle of 0. Once I know what the voltage is across all of these components, I can find the current through any of these components. So the current through the capacitor would be the voltage over the impedance of the capacitor, and the current through the inductor would be the voltage over the impedance of the inductor. The voltage is 1.8, phase angle of 0. The capacitive reactance is the same as the inductive reactance, so it's 200 ohms with a phase angle of -90, and I end up getting that the current is 9 milliamps with a phase angle of 90 degrees. And oops, I can go through the same process. Of course, the only difference between the capacitor and the inductor is the phase angle, because they have the same reactance, so it would be 9 milliamps with a phase angle of -90. So they are exactly 180 degrees out of phase. When one is positive, the other is negative, and essentially those two currents entering the node, like if you look at the current that's coming out here, it will always, out of this node here, between these two components will always be 0, because they're always canceling each other out. Let me go back for 1 second. And the other thing which I didn't do is I could use the quality factor. So remember that our quality factor was, oh, I can't go back that easily, but our quality factor was, what was it, 2.5, I think it was. And so these currents reflect the fact that they are related to the current of the source, right? So if I take the current of the source, 3.6 milliamps, and I multiply by that quality factor, I should get the current through each of those different components. I can determine the bandwidth for my particular resonant circuit. It's just going to be the difference between the upper half power frequency and the lower half power frequency. I know that in general that's 1 over the resistance times the capacitance. So I can plug those values in, and I get that the bandwidth is 5,000 radians per second. I can make a sketch of what the voltage response would look like in this circuit. So how does the voltage change across those components? And I can also do that in terms of the power. In order to do that, I really should figure out what those half power frequencies are so I can make a good picture of what's going on. So I can determine the lower half power frequency and the upper half power frequency by plugging in the values that I have in my circuit. And I've left off a lot of units here. But I end up finding that the lower half power frequency is 10,247 rads per second, and the upper half power frequency is 15,247. So I can at least plot those values, and I realize that the bandwidth, of course, here is going to be a difference of 5,000, right? And of course, here's where that comes from. If I take the difference between these two, I get a difference of 5,000. If I wanted to use the approximate half power frequencies, I realize that the approximate lower half power frequency is just half the bandwidth, well, taking the resonance frequency and subtracting half the bandwidth, and then taking the resonance frequency and adding half the bandwidth should give you an approximate value for the upper frequencies. And if I do that, I get some values that are pretty close. So I do have to be careful when I use that. Sometimes, depending on what the bandwidth is, it might not give us values that are close enough to use. So if I were to make a sketch of this, my voltage is a maximum at 1.8 volts. That occurs at 12.5, and that's kilorads per second. And then there's my lower half power frequency and my upper half power frequency. And I realize that those occur when the voltage is just essentially the effective voltage, right? So 1.8 over the square root of 2. And here is also my response in terms of my power. We didn't calculate what the power was at the maximum, what the maximum power was. We certainly could have done that. We could have taken the current, which was 3.6 milliamps squared, and multiplied by the resistance of 500 ohms, and we would get that 6.48. And then we could go back through and we could plug in what those upper and lower half power frequencies were in our circuit, and we could have determined what the voltage was and the current, and gone ahead and made sure that that really was our half power frequency. We've done that for some examples with series resonance, and the process is still valid using parallel resonance. All right, let's consider another example. It's called a tank circuit, where we actually consider the fact that the coil has resistance associated with it. And we want to calculate a number of things, and we're going to start by calculating the resonance frequency. So the first thing that I realize is that, that my coil does have resistance, and so I can't ignore that. So I need to figure out what the parallel resonance frequency is, and I need to consider what that coil resistance is. And so I can go ahead and I can plug my values in. And I realize that the term out front, so when I multiply the inductance times the capacitance, my inductance is 1 millihenry, 1 times 10 to the minus 3. My capacitance is 1 nanofarad, 1 times 10 to the minus 9. And then I take the square root and the inverse, I get a really big number here, right? So this resonance frequency is like 1 times 10 to the 6. The other thing I realize is that the terms under the square root, I did this on purpose. When I take the coil resistance squared and then I divide it by L over C, I get this number that's 1 times 10 to the minus 4. So 1 minus 1 times 10 to the minus 4 is essentially 1. So in this particular example, the coil resistance squared is much, much less than L over C. So for all practical purposes, I could have used the expression that the resonance frequency is just 1 over the square root of the inductance times the capacitance. So it's essentially 1 times 10 to the 6 rads per second, or 1,000 kilораds per second, or 1 megarad per second, right? So we can use different prefixes there to write down what the resonance frequency is. I can also determine what the quality factor is of the coil at resonance. So this is not the whole quality factor of the whole circuit, it's just the quality factor for the coil. And so looking at what this inductance is, what this coil resistance is, I can actually determine for the coil what is the quality factor. And it's just the resistance over the inductive reactance. And so this is 10 ohms over the angular frequency times the inductance. It's a very, very small number, that quality factor for the coil. So I guess that's a good thing, because that's really telling us that coil resistance in this particular case is something that we do have to consider, but it's not having a big impact on our quality factor for the coil. So in order to analyze this picture, I have to take my pure inductance, which is in series with this coil resistance. So everything here in this blue box is the actual inductor, right, with the coil. But we have to separate those out and write them as a purely inductive component and a purely resistive component in parallel. And I know that I can do that using the transformation from a series resistive piece with an inductive piece into a parallel piece for a resistive and an inductive piece. So my coil resistance is 10 ohms squared. I can put my reactance in here and divide by my resistance to get my parallel resistance, equivalent resistance, and I can do the same thing for my inductor, and I can find the inductive reactance that would be in parallel. And I end up getting, for the resistive piece, that it's about 100,000 ohms or 100 kiloohms. And for the inductor, I get the inductive reactance is about 1,000 ohms or 1 kiloohm. So that means that my picture that I started with is equivalent to a parallel resistance of 100 kiloohms. It's in parallel with a reactance of 1 kiloohm. And I realized that if I know the reactance of my inductor, I also know the reactance of my capacitor, because at resonance they would be equal to one another. And then I still have my resistance in the circuit. So I'd like to analyze this circuit, and I'd like to look at, maybe what the current is through the different components, what the voltage is across of the components. And in order to do that, I need to combine the resistor that was a part of the coil with the actual resistance that's in the circuit that is just a resistor in the circuit. So I have 25 kiloohms that is essentially in parallel with this 100 kiloohms. And so I can combine them as an equivalent resistance. I'm not really worried about the impedance value right now because I'm only combining resistors in parallel, and so I'm just treating them as just resistors, right? So I can combine those two values together and I get an equivalent resistance of 20 kiloohms. So I can redraw my picture as being my current source with an equivalent resistance of 20 kiloohms. I have a capacitor that has a capacitive reactance of 1 kiloohm and an inductor which has an inductive reactance of 1 kiloohm. So now that we have our equivalent circuit for resonance and we have components that are connected in parallel and we have an equivalent resistance, our capacitor and our inductor, we can solve for the voltage across the capacitor at resonance, and we have to keep in mind that, that these are all connected in parallel. So if I can calculate the voltage across the resistor at resonance, then I also know the voltage across the capacitor at resonance, and for that matter I know the voltage across the inductor and I know the voltage across the current source. So at resonance, all of the current from the current source goes through the resistor because the impedance values for the capacitor and the inductor cancel out. And so this would be the current of 200 milliamps, not 200, excuse me, 20 milliamps, phase angle of 0, times 20 kiloohms, phase angle of 0, and I get 400 volts with a phase angle of 0. I could also determine the current that's going through the capacitor. This is a misprint. This should be the voltage across the capacitor over the impedance of the capacitor. And so this would be the voltage, which is 400 volts because it's the same voltage across all of the components, over the impedance of the capacitor, which is 1 kiloohm, phase angle of 90, and I get 400 milliamps with a phase angle of 90 degrees. So even though this circuit is at resonance, parallel resonance, and even though the current source, all of that current goes through the resistor, there is still current that is going through the capacitor, and it's a very large current, right? It's significantly bigger than the current of the source. Now, of course, there's also current through the inductor, and I could go through the same process because there's voltage across that inductor and it has impedance, and it's also 400 milliamps at resonance. These two currents are exactly the same value, but they are exactly 180 degrees out of phase, so that when one is positive, the other is negative, and they always cancel each other out. So 200 amps enters, it gets to this junction, all of it goes through this resistor, but there is still current through these two components, and they're basically such that if you look at the current that's coming out of the node that connects these two, it's always going to be 0 at resonance. We could determine the bandwidth for this particular circuit as well. So the bandwidth, of course, is just the difference between the upper half power frequency and the lower half power frequency, but we know that's just 1 over the resistance times the capacitance. So that's 1 over the resistance is the equivalent resistance, so 20 kiloohms is 20,000 ohms, and times 1 nanofarad, which is 1 times 10 to the minus 9, and I get that this is 50,000 rads per second, or 50 kilorads per second. I can sketch the response curve for this, or the power curve. I didn't actually calculate the power, maximum power, half power, but we could do that, again, similar to ways that we did that for series resonance. I can calculate the approximate half power frequencies just to sort of see where we stand. So I would take the resonance frequency, subtract half of this bandwidth, and see what I get, and I can do the same thing for the upper half power frequency, where I would take the resonance frequency and add half of the resonance frequency. So the resonance frequency was 1,000 kilowatts, not kilowatts, sorry, kilorads per second. And so I can subtract half of the bandwidth. Half of the bandwidth is 25. And I can add half of the bandwidth. Wow, So that should be a positive there, right? Not a negative. And I end up getting that the lower half-power frequency is 975 kilораds per second, or 0.975 megarads per second. And the upper half-power frequency is 1025 kilorads per second, or 1.025 megarads per second. So here is my response curve and what it would look like. There is the maximum voltage, which is 400 volts, because that is when my impedance value, when all of the current goes through that resistor, so I'm going to have the largest voltage. And then at the lower half-power frequency, the voltage should be basically the voltage over the square root of 2, and then I also get a value on the other side, and I have a bandwidth of 50 kilorads. So this axis is in millirads per second. So just keep in mind that from looking at series resonance, that a lot of those calculations that we did a little more details with, that you can do those same things here with parallel resonance. So we could calculate the half-power frequencies and then plug those back in and figure out what the impedance is at those locations, or those particular frequencies, and then we could certainly calculate the power as well.